Hello everyone, this is module 11 lab. In this lab we have two tasks. Task 1 is a programming exercise and task 2 is about modular programming, in which we try to compile and run multiple files using shell script and using make tool that we have learned in module 11. So in task 1 we have been given two exercises, exercise A and exercise B. In exercise A, we are asked to take a look at two files, first ASM and second .asm, that is being given for this lab to us, and we are asked to describe what this modular programming does. Basically, there is a program that consists of these two files, and we have to take a look at the content of these two files and analyze the content of the program and say what this program do. Okay, let's take a look at those files. So here is file number 1, which we call first.asm, and it is very similar to the ASM template that we normally use. So here is the main program, and as you can see from the top, we have defined two external variables, meaning that these two variables are defined in a different file. And since for this program we have two files, probably they are defined in a second .asm that we will take a look at. Okay, so what this program does is very simple. It takes the content of variable 1, which is a memory indicator or memory pointer, and it store it in EAX register, and then we call print int and print whatever value is in the memory at location variable 1. So we'll see what the variable 1 is from the second file .asm. So if we switch to the second file .asm, we will see that variable 1 is defined as a double word value, and the value is 22. So upon execution of this program, when the program reaches at this point, is going to take that 22 from the content of variable 1 memory pointer and print it out. This is just to show you how to define an external variable and how to access it from a different file. So basically the keyword extern help us to do that. So the second one, second extended variable is fact. It happens for the fact to be a function. So if you take a look at this, we are calling fact. It means that this is a subprogram or function for this exercise. And if we investigate the content of second ASM, we'll see that this label fact basically is a function that consists of this line from line 12 to line 32. So we are doing some processing over here, and once we use the call function, once it reaches here, return, it's going to return back to the first.asm and continue compiling the program from line 22 to line 29, where the program will be completed. Okay, so our task is to investigate the content of the call fact and see what it does. So when we are looking at basically fact function, we will see that we have multiple locations where the program deals with stack. One of them is inter 00. So as we have discussed this previously, inter consists of 3 different tasks. So push EBP, move EBP, ESP, and sub ESP number of bytes, for which with this program number of byte is 0. So therefore, for this program, inter 0, 0 consists of 2 assembly syntax. So let me write that down in here. So inter 0, 0 is equivalent to push EBP and move EBP, the value of ESP, whatever that value is. Okay, we know that right now, and we know that push syntax impact the stack layout. So let's go back to the program and find out what the program is doing. So since the program deals with stack, the best way to analyze and understand what it does is to draw the stack layout as we go through each line. So we have done this before, but I'm going to do the stack mapping and drawing for multiple lines for this program, and I'll let you do the rest. Let's go back to the first .asm, the first file. So from here, we know that it's just program and calling the value of variable 1, putting that in EAX and print the value out. Since these are a function, it means that upon completion of that function, the stack won't change. And here we start drawing the stack from this point, line number 20 to line number 22, to understand what the function fact is doing. Okay, the first thing that it does, we push number 6 into the stack, and then we call fact function. So push going to store number 6 in the stack, and call fact is going to store the value of the return address, which is the address for this syntax, line number 22. It pushes that on the stack, and then we move on to the fact function, which is our function defined in second.asm. So let's take a look at the stack up to this point, line number 12, and then we take it from there, and we will see how inter is going to impact the stack. If we're going back to this figure, so I've already drawn the stack here. So we push line number 6 in here, and then we call function fact. So that function fact is going to restore the address, to store the address number 22 in the stack. And then we come to this line inter 0, 0, which is equivalent to this 2 line. So what it does is push the EBP in here, and we move to the next line. Next line says EBP ESP. So ESP right now is pointing to this location, and EBP probably is somewhere in here. When this line is executed, move EBP ESP, then basically here's the ESP. Then EBP also is going to point to this memory location. So EBP. So we are creating a new stack frame. Let's move on to the rest of the function and see what's happening. Okay, following up on this, so we see that we are moving the content of EBP plus 8 to EAX. We go back to the stack and take a look at the content of EBP plus 8. EBP right now point to this location. Right, so EBP plus 4 is going to be this location, and this one, and EBP plus 8 is going to be this location number 6. It means that number 6 is going to go to register EAX, because that's where right now EBP plus 8 is pointing. So at this point, number 6 is going to be stored in EAX. Then we compare number EAX register with value 0. If it is greater, we jump into the recursion function here. In the recursion function, we decrease the value of EAX, So EAX is 6, it's going to be 5, and then we push that value into the stack again. So now we come back to the stack here, and we push the value of EAX, which is number 5. Why? Because we decrement it, right? So now we do that. So ESP right now point to this location. Okay, now go back to the program again and see what the next line is. Next line is again call factorial. So right now we are in the factorial, we are in the fact function, and again we are calling fact. So therefore this is a recursive function, and we have explained this in previous lecture. So we are calling the function with it itself. So what happened in here is upon calling the return address, which is the next line after the call function, line number 26, is going to be stored in the stack, and the factorial function or the fact function is going to be executed again. So we go back to the stack, we put the return address there, return address, which is line number. I use line number, but in the real system it's going to be the address of the memory which stores basically this line of code. For simplicity, I put 26 in the stack, so return address 26. So now my ESP is pointing to this location. So then again, the program is going to the beginning of the fact function, which is enter 00, and we have again these two lines of code. So what we do, we push EBP, and same thing again. So EBP and ESP will be pointing out to this location once we execute these two lines, which are equivalent to enter 00. So now we are again calling the fact function, and we are at this point, and the next thing to do is EBP plus 8 to EAX. Let's take a look at EBP and EBP plus 8 and see what the value of EBP plus 8 is. So we go back to the node. This is the value of EBP. EBP plus 4 is this one, and EBP plus 8 is number 5. So what we do, we are taking number 5 and we store it in the register EAX. So what happened next is we compare that value with 0, and since it is greater, we jump into the label recursion here, right? So and in there we decrement the value of EAX and push that value of EAX into stack. Now the value of EAX is 5, we decrement it is going to be 4, and then we push the value of 4 into the stack, and then again we call the fact function. So the value 4 is going there, and the return address 26 is going to be again stored in the stack, and we go to the fact function. We're going to execute this intern line enter 00, which is push EBP, move EBP ESP. We execute that again, and then EBP new value is going to be stored in the stack, and then we take that value of EBP plus 8, which is this time 4, and 4 is going to the register EAX. So I do not draw the rest of this. It is going to be similar until the value of EAX is 0. So once the value of EAX is 0, we are not going to jump to recursion. What we do, we are going to basically to move number 1 or initialize EAX with number 1, and then we jump to end factorial. So in end fact, what we have is syntax leave, which syntax leave is equivalent to pop EBP value, right? So it's pop EBP value, and then basically what we do in the stack, we are restoring back the previous value of EBP from the stack. And what happened after that is the return function. So the return function, when it execute, it go back to the stack, take a look at the return address, and we know that the return address that we stored in the stack was one of this line, for example line number 26. So we take that value, and that value is going to EIP register. It means that the next instruction that will be executed is line number 26, which is add ESP plus 4. What it does, basically, it takes the ESP pointer to the location below that return address. So it basically destroys one element from the stack, and then what it does, it multiply EBP plus 8 by whatever value is in EAX. The current value for the first round that is in EAX is 1, and the previous value which was there in EAX is also value 1. So this time, the first time, the IMAL gonna be multiplying 1 by 1. So once it is done, the value of 1 by 1 become 1, and it's going to be stored in EAX register. And then we come again to end fact leave, which this time will pop out the value of the stack, which is the previous EBP value, and restore that. And next is going to the next line, which is the return going to take us to this add instruction. It means that it's going to be removing one of the elements from the top of the stack, and going to this time multiply the value of the EAX, which was again 1, and multiply it by EBP plus 8. So this time it's going to be multiplying that with number 2. And this process, it will be repeated until we reach to the last return address in the stack in here. So the last return address is going to be line number basically 22, and the last value on the stack is number 6. So if you follow those trends, you will see that our multiplication going to be something like this: 1 multiplied by 1 multiplied by 2 and 3, 4 and 5 and 6. So basically this is the value of 6 factorial. So once we basically we get to this point, this return address is going to be related to the first.asm, which is our last return address. So once we are in this program, so the last one was related to this, and upon that the execution, the return address store is pointing to us to line number 22, which is in here. So add ESP number 4 is going to remove the last element from the stack. So it's going to remove this element from the stack, and basically the ESP pointer is going to be pointing to one element below that, which was the original stack layout in our main function. So if we go back to our first SM function again, so then we call print int, and it's going to print out the value of EAX, which right now at this point is the value of the factorial, the 6 factorial, right? And then print new line. So basically what this function does is, what this program does, it does two things. It prints out the value of the variable 1 from the second file, which was number 22, and it comes and compute factorial of 6 in a recursive way, which we explained in module in previous modules. Okay, so that's how it is. So in this task, you are required to basically complete this stack layout. So I did it for a few numbers and explained how it goes up to the end number 0 for EAX, and from there it's going to go back down from the stack and start multiplying that number until it reaches to number 6. So complete this and include it in your report. Now let's go back to the second task. So second task is about modular programming, compilation and run. We have gone through this basically modular programming, compilation and run from the beginning of our course, starting from module 3, that we have created a shell script for the run, and we automate the compile and run process, and it saves us a lot of time. In module 11, we learn a new utility called make tool, that it has some advantages over the shell script that we have explained in module 11. So in task number 2.1, we are asked to write a shell script to compile all the source file in task 1 and produce the executable. We call our shell script run modular.sh, so we create a file like that. And as explained in here, this file is like run.sh script, which we have used before. The only difference is that right now we have 2 additional files. So let's take a look at this one and see what those 2 additional files, how we could incorporate 2 additional files in the run program. And then we talk about task number 2.2. You go back in here, I have my run.sh stored in here. This is the file basically that we have before, right? It was kind of parametric, and in that we had one argument, which was the name of the file. So right now we can easily update this and create our run modular.sh. So what I do, I add my 2 files in here, first.sm, and then I compile to create my second file, which again it was the second.sm. So that's my file, and I say and then I create gcc -m32, and I don't have $1 because this run modular, I'm not going to make it parametric. I just want it to be run for this specific task. So I call my file name, maybe I call it output, and then basically the number of object file right now is not only 1, so we have 2 other object file, first.o and second.o. So I'll add those 2, second.o and first.o as well. Now I added 2 extra object file because why? Because I have added into this shell script 2 ASM file. And then I call my binary output, and I can add that line to execute this output file again. So if you save this and include this run.sh run_modular.sh file into your current directory and just run it, it's going to compile these 2 files along with your libraries and driver.c and eventually run your file easily. Okay, next task in this lab is related to makefile. Makefile, the difference between makefile and run.sh or shell script that we have used before is that run.sh is kind of down to top, having a down to top architecture. Makefile is different in a way that it does this, and we explained that in a lecture. But let's quickly take a look at the makefile for this particular example and see how we can run it. Here is the makefile structure for this example. So as you can see here, the output of the main output going to be a file name called out. So makefile eventually is going to do all these tasks to be able to run the executable file that calls out. So if we look at the first line, basically the program is going to be running out, generating out, how? Using the syntax that is given in here. So it's run that, its output going to be file out, and its input to this syntax is going to be this file. Then how it's run it? It's run the GCC and GCC options. Our GCC option is -M32, and it's gonna produce a file name, basically should be out. Our file name should be out, and it takes driver.o, first.o, second.o, and sm.o. So the makefile utility then will look for this file and see how it can generate this file. For first.o is going to be generated using this syntax NASM, and the input to that NASM function are these two files. So first.asm and asm underline io.inc. Why we are having this? Because this is included in the first.asm file, and that's the reason it's one of the library that we need to have aligned with the first.asm to be able to generate the object file using NASM syntax for it. So if you investigate first.asm, you will see that these files in here. So that's the reason when you're doing the makefile, you have to include that library in it. Same things for second.io. When we are generating that, we need this library file as well when we are doing the NASM basically syntax to generate that object file. So we generate the first.io using the NASM syntax here. We create the second .io using the NASM syntax in here, and then we also need the object file for asm_io.o, and its input going to be only this NASM, this asm file, and the syntax that we will using to generate that output object file is line number 13. And eventually for driver.o, which is our object file, the input to our function gonna be driver.c, and how we generate that object file using GCC syntax and driver.c. So once we have collected all these first, second, sm, and driver object file, we plug it, the make utility will plug it to this syntax, and eventually we'll generate the out binary in here. So that's that. So then once you have this file, you run the make syntax, and then that will be generating the out file for you, which eventually you can run it and see how your makefile compile and run your factorial function that we explained in this program. So the deliverable for this lab are the following. You need to write the lab report, attach the cover sheet, explain a paragraph or two for each of these tasks, include your the stack layout that you draw, and include it in your report, and provide some explanation how the stack grows and how it goes back to its original layout after running the function. And then include your two file, makefile and run modular.sh script with your report. These conclude our lab number 11. Thank you for watching.